Hi all, let's take a look at section 4.4, Laws of Logarithms. Now, as I say here in the beginning, these law of logarithms are going to be used throughout the rest of your math classes. You cannot ever forget the laws of logarithms. There will be times in calculus where we're dealing with certain things like these. Sometimes you'll need to condense using laws of logarithms, and sometimes you'll need to expand. So let's first start there. So whenever we deal with laws of logarithms, you have three major rules. The first rule says that anytime you have a product inside of a logarithm of any base, notice this base A is supposed to represent any base. Well, anytime you have a product on the inside, you can separate that up into two separate logarithms. So the log base A of u times v is the log base A of u plus the log base A of v. Now, since that log is of any base, most commonly we use the natural log, so you could also say, as I said over here, or just the natural log of the natural log of u plus the natural log of v is equal to the natural log of the product uv. So here I have the product within. Whenever I separate them, it's two separate natural log functions of natural log of u plus the natural log of v. Remember, these two are the exact same rule. It's just in this direction I'm doing condensing, in this direction I'm doing expanding. Over here I had any generic base A, and this is specifically the base E. Anytime it's base E, you use the natural log notation. Now, for the next one, well, what if I have a quotient inside of a logarithm? So the log base A of u over v. I can say, well, anytime you have a division or a quotient, you can separate them up through subtraction, and that should make sense. If you separate multiplication by addition, then you separate division by subtraction. So you see in this case it's going to be the log base A of u minus the log base A of v. And then I said over here, well, okay, what if we had in terms of natural logs? Out as an expanded expression, you could say, well, the natural log of u minus the natural log of v is equal to the condensed expression, the natural log of the quotient, u over v. Now, anytime you have a power on a term inside of a logarithm, then that power can come out in front of the logarithm, and I can say, well, the log base A of u to the n, it's the same thing as n times the log base A of u. And notice over here in natural logs, I can say n times the natural log of u is the same thing as the natural log of u raised to the n power. Now, I wanted to make sure I made this special note here because this is a mistake I see often. That power can only come down in front of the logarithm if it's only on the term inside of the logarithm. So yes, the natural log of u to the n is equal to n natural log of u. But what if I have the n on the entire logarithmic function? So it's not just on the term inside the logarithm, but it's on the entire logarithm. In that case, you cannot say, and please understand the difference between this and this. Here the n is on the entire logarithmic function. You can't call that n times the log base A of u. It's only if that n is just on the term on the inside of the log that rule can be used. Okay, now let's look at some examples. So in this one, we're asked to expand these logarithms. So expansion is when we're going from the condensed version. In condensed version, terms are always multiplied, divided, and you have powers. In expanded form, you don't have any of those. You have no multiplication, no division, and no powers. So we're asked to expand so that you have no factored products, quotients, or powers on their factors remain. Okay, so we have the log base 4 of 16 a cubed on the square root of b. So I went ahead and broke that up. I noticed I had three terms being multiplied inside of that log base 4. So notice, log base 4 of 16 plus log base 4 of a to the third plus, notice what I did here. I went ahead and said that square root is the 1/2 power, so that's plus the log base 4 of b to the 1/2. I didn't have to do that, but it helps because I know that in the next step I want to bring that fractional exponent out in front. It's a lot easier to see when you do that as opposed to leaving the square root. Now I can simplify and say, well, this first term, 2. That's simply because I was saying I know the log base 4 of 16 is 2, because that is literally asking me, what power would you have to raise 4 to in order to get a 16? 4 to the second power is 16. That's why that answer is 2. Of course, you could also take the wimpy way out and use your calculator and say, calculator log base 4 of 16, and get your 2 that way. But you'd just feel weak using your calculator when you can just look at it and say, hey, I know that 16 is the second power of 4, so that answer is 2. The next one here, I bring the exponent 3 out in front and call that 3 log base 4 of A. And the last one, I bring that 1/2 out in front and say plus 1/2 the log base 4 of B. Now, for the second one, and notice that's the final answer, because inside these logarithms, and the first term simplified out of the logarithm, you don't have any products on the inside, you don't have any powers on the inside, you don't have any quotients on the inside. That's how I know it's fully expanded out. The next term, I have products inside, I have powers inside, and I have a quotient on the inside. I've got to simplify all of that inside that natural log. As soon as I look at it, I see I'm going to have 1, 2, 3, 4 separate logarithmic functions. The x and the y squared are going to be inside logarithms being added. The 5 and the z cubed are going to be inside logarithms being subtracted, because they're both being divided. So pretty easy process to break up. I just say it's the natural log of x plus the natural log of y squared minus the natural log of 5 minus the natural log of z cubed. From that, you just say we're going to use that last step that says any power can come out in front. The first one didn't have a power, so it just stays the natural log of x. Second one becomes plus 2 natural log of y. The third one cannot be simplified because the natural log of 5 is an irrational number, so I would just leave it like that. And the fourth one, that 3 can come out in front and have it minus 3 natural log of z. Now, keep in mind, the reason I didn't do anything for that natural log of 5, it's like I said, it's an irrational number. Anytime you have an answer like that to a logarithm, it's better just to leave it in the exact form. Okay, next. So on this page, I'm looking at going in the opposite direction. In the previous problem, I expanded the logarithm. Now I'll give you a logarithm in expanded form and ask you to condense. No problem. We say, well, we know that any powers out in front of a logarithm can go into the term inside the logarithm. So I can bring the 4 up into the power here. I could bring the 3 up into the power here, and the 9 up here. That's all I've done in this first step. I have the log base 2 of x to the 4th plus the log base 2 of y cubed minus the log base 2 of z to the 9th. And then you say, well, okay, now I need to write them as all one logarithmic function. No problem. Any of the logarithms being added, those terms belong in the numerator of the combined logarithm. Any logarithm being subtracted, the term inside that logarithm belongs in the denominator of the condensed logarithm. So this log base 2 of x to the 4th y cubed divided by z to the 9th, final condensed answer. Let's look at one involving natural logs. It's the same idea. I automatically know I'm going to have 2 terms in the numerator because I have 2 positive logs. Then this term is going to be in the denominator. It's going to be because it's a log being subtracted. Before I worry about the quotient, I'll go ahead and say, well, let's deal with the coefficients. That coefficient of 1/2 goes up as a power on that 36. That coefficient of 2/3 goes up as a power on the 27. And then I just had to think, well, 36 to the 1/2 power, that's the same thing as the square root of 36, which we know is 6. Then I have plus the natural log of 3, and then the natural log of 27 to the 2/3 power. All you have to do is think, well, it's the cube root of 27. Well, the cube root of 27 is 3, and then you need to square that answer. So this is the cube root of 27, which is 3, and then 3 squared is 9. Of course, you could take the wimpy way out and say 27 raised to the 2/3 power and get your 9 that way. But of course, you don't want to do it the wimpy way. You just want to look at it and know, hey, it's the cube root raised to the 2nd power. Of course, it's 9. Now, whenever we simplify here, we can say this is the natural log. These two terms belong in the numerator as a product. This one's divided in the denominator. So I have 6 times 3 is 18. 18 over 9 is going to give me a 2. This final answer is the natural log of 2. And again, I would prefer just the exact answer as opposed to a decimal approximation there. So I'd leave my answer like that. Up next here, again, I'm wanting you to condense down to one logarithmic function in terms of log base 3. So in this one I have 6 log base 3 of a minus 1/3 log base 3 of b plus 9 plus the log base 3 of c minus 4. So you can say, well, again, I know I'm going to have 2 of these logarithms terms are going to end up in the numerator because this is a positive log, this is a positive log. The term inside this logarithm is going to end up in the denominator because that log is being subtracted. First step first, though, I'll go ahead and move each of the coefficients up as exponents inside of my log. So I have the log base 3 of a to the 6th minus the log base 3 of the group b plus 9 to the 1/3, and then plus the log base 3 of the group c minus 4. Now, the only thing I've done from the first step to the second step is I just rewrote that 1/3 power as the cube root. We know it's the same thing. And I kept everything else the same. Now, from this step to the next, I said, let's go ahead and condense these down to one logarithmic expression. Any of the terms that were being added, those terms inside the logarithm get multiplied in our condensed logarithm. So we have the log base 3 of a to the 6th times c minus 4, all divided by the term inside the logarithm that was being subtracted, so divided by the cube root of b plus 9. Now you're thinking, hey, that's not bad. It's really not. Law of logarithms is pretty straightforward stuff. The last thing I want to talk about is the change of base formula. With our calculators, it's really not a mandatory formula anymore, but sometimes it might be just quicker to use the change of base formula than using that log base button on your calculator. So if I'm trying to determine the log of any base a of b, I can say, well, I can take the log of any base of the number on the end. Now, I just changed the base c just to show you that it doesn't have to have the same base as whatever the original base was. I can say I can take the log of any base of the number on the end divided by the log of any base of the number on the base of this logarithm. So more specifically, if I say, well, okay, since I can take the log of any base of these two numbers, how about I take the log of the two easiest bases? We both have, or we all have a log and a natural log naturally on the calculator. So if I wanted to take the log of any base a of b, I could just say it's the common log base 10 of b over the common log base 10 of a, or I could say it's the natural log, which is log base e of b over the log base e of a. Let me show you that in a problem here. So if I'm asking you to evaluate the log base 14 of 83,955 using the change of base formula. Now I already have the answer here, but let's show where that comes from. So this is literally asking you, what power would I have to raise 14 to in order to get 83,955? Pretty cool problem. So first of all, if I did it just the calculator way and just typed in the original, I would have to use the math, and then you'll arrow up to log base. It's quicker to arrow up than it is to log down. So it's math, log base, and then you just type in the base 14, you arrow over 83,955 in this case, and you can say, okay, hit enter, and we get our 4.29625. Oh, actually, that wouldn't round up to 5, would it, guys? It'd stay a 4, so I need to correct that. So 4.29624 would be the actual answer there, rounded to 5 decimal places. But now I can say, well, okay, let's find this answer 2 other ways, just to show. So let's say you had a calculator that doesn't have that change of base, that log base button on there, or else you just didn't remember that. There's no need to remember it. You could simply just say it's the log of 83,955. Have to remember to close that log off. Divided by the log of the base of that logarithm, 14. Notice you get the same answer. Or also you could say, well, what about the natural log? No problem. Natural log on your calculator right here. I would just say it's going to be the natural log of the 83,955 divided by, make sure you close off that natural log, then divide by the natural log of 14, close, and you'll notice you still get that same answer, 4.296244759, no matter what, which rounded to 5 decimal places is going to be the 4.29624. Now, whenever we look at this answer, you say, keep in mind, every single time, a lot of people lose sight of what they're doing whenever they do a logarithm. I don't want you to be one of those people that say, yeah, okay, that's the answer. I don't know what it tells you, but that's the answer. Please remember, the answer to any logarithmic function, it's simply telling you what number you have to raise the base of that logarithm to in order to get the number on the inside. So if I wanted to check this, all I would have to say is 14 raised to that answer I just got, and I hit second negative to pull up the answer. 14 raised to that answer better be 83,955. And if it's not that, I won't ever test you over this. But notice, it is! So that means you will get tested over this. Haha. So, gorgeous stuff. Whenever we look at these logarithms like this, please keep in mind that all you're doing, the answer to a logarithm, it's just the number that you have to raise that base of the logarithm to in order to get the number on the inside. So absolute gorgeous stuff here. Please let me know if you have any questions in this section. Now, after looking at the laws of logarithms, what we'll get to do is start working out equations with logarithms and exponentials in them. Fun stuff.